Hi there, this is Professor Shannon Gracie. Today we'll be covering complex zeros and the fundamental theorem of algebra. This is section 4.3 from Sullivan and Sullivan's Precalculus Enhanced with Graphing Utilities. So let's go ahead and take a look at the warm-up. We're finding all complex zeros. So basically, remember how we were throwing out results that would have had an I in them. So now it's okay to have imaginary numbers as part of your answer since we are in the complex number system. So pause the movie, warm it on up, and see how you do. Okay, let's see how you did. So if we set f at x equal to 0, we will get I think I'll just use the quadratic formula on this one. So x is the opposite of b, which is -1, plus or minus the square root of b squared minus 4 times a, which is 5, times 2, all over 2 times a. So x will be 1 plus or minus the square root of 1 minus 40 all over 10. And then we will have x is 1 plus or minus the square root of -39 all over 10. Now remember, if you have a product within a radical, you can split it into the product of two radicals. So we'll get x is 1 plus or minus the square root of 39 times the square root of -1 all over 10. And the square root of -1 is I, so we will get 1 plus or minus root 39 times I all over 10. Rewriting in the form of a complex number, we'll get 1/10 plus or minus root 39 over 10 times I. So our solution set will be as so. How'd you do? Awesome. Okay. Complex polynomial functions. A variable in the complex number system is referred to as a complex variable. A complex polynomial function f of degree n is of the form f at x is equal to a sub n times x to the n plus a sub n minus 1 times x raised to the n minus 1, all the way down to a 1 times x to the 1 plus, a 0. So it's the same format as a regular polynomial, but you could have complex variables in there. So a sub n minus 1, those are in the complex number system. A sub n is not equal to 0, n is a non-negative integer, and x is a complex variable. So a sub n is still called the leading coefficient of f, and a complex number r is called a complex zero of f if the function evaluated at r is equal to 0. Okay, so remember that the real numbers are a subset of the complex numbers, so you can have a mixture of complex coefficients and real coefficients. Now, the fundamental theorem of algebra says that every complex polynomial function f of degree n greater than or equal to 1 has at least one complex zero. Sorry that it's offset like that. So this brings us to the next statement, okay? This next statement, I'm going to do the proof above it, but this next statement basically says Every complex polynomial function of degree n greater than or equal to 1 can be factored into n linear factors. They're not necessarily distinct, of the form f at x is equal to a sub n times x minus r1 times x minus r2 dot 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 times x minus r sub n, where a sub n, r1, r2, all the way down to rn are complex numbers. So what does that mean? Every complex polynomial function of degree n greater than or equal to 1 has exactly n complex zeros. So before we were finding real zeros, and we didn't always have as many zeros as the degree of the polynomial, but you will always have as many zeros when you're as the degree of the polynomial when you're in the complex number system. And that's what this is saying. And you could have repeated zeros. So let's take a look at the proof for this. So let f at x equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a1x plus a0. Now, by the Fundamental Theorem of Algebra, which is the theorem above, we know that f has at least one zero. In the complex numbers, call it R1. Then, by the factor theorem that we learned previously, x minus R1 is a factor. And we could rewrite f at x as some quotient, some first quotient in x times x minus R1. Now, if you repeat this argument n times, you will have f at x is equal to some nth quotient in x, which will be the zero polynomial, times x minus r1 times x minus r2, all the way till you get to x minus rn. And like I said, where q sub n at x is a complex polynomial function, of degree n minus n, which of course is 0, and whose leading coefficient is a sub n. So f at x is equal to a sub n times x minus r1 times x minus r2 all the way down to times x minus r sub n. And this function here has exactly n zeros, which is what we wanted to show. So we're done. I mean, with that proof. Okay, so here we go. The conjugate pairs theorem. Let x be a polynomial function whose coefficients are real numbers if r equal to a plus b times I is a zero of f. The complex conjugate r equals a minus b times I is also a zero of f. So let's take a look at a problem. So find a polynomial function f of degree 4 whose coefficients are real numbers and that has the zeros negative 2, 1, and 2 minus I. And then we can use our graphing calculator to verify. So, okay, let's just list out our zeros. X equals negative 2. X is 1. X is 2 minus I. So what's the complex conjugate of 2 minus I? Good. X is 2 plus I. So adding 2 to both sides, we'll get x plus 2 is 0. Or x minus 1 is 0. Or x minus 2 minus I is 0, or x minus quantity 2 plus I is 0. So using the zero product property in reverse, we have x plus 2 times x minus 1 times x minus quantity 2 minus I times x minus quantity 2 plus I is 0. So if we let that equal to our function f, that left side, and then just continue to multiply out, we'll get a polynomial that meets these requirements. So let's multiply x plus 2 times x minus 1 first, and we'll get x squared minus x plus 2x minus 2. So this is this times we'll have x squared minus x times quantity 2 plus I minus x times quantity 2 minus I plus 2 minus I times 2 plus I. So that this guy is the second one. And then we just continue to simplify. So f of x will be equal to x squared plus x minus 2 times x squared minus 2x minus xi minus 2x plus xi. And then the second one is a difference of squares, so we'll have plus 4 minus I squared. So f at x will be x squared plus x minus 2 times x squared minus 4x. The xi zero out, so these guys zero out. And then we'll have I squared is negative 1, right? So this here is negative 1, so 4 minus negative 1 is 5. And then, just multiplying these two together, we will have f at x is x to the 4th minus 4x cubed plus 5x squared plus x cubed minus 4x squared plus 5x minus 2x squared plus 8x minus 10. And putting it all together, we will have x to the fourth. We have two terms with cubes in them, so that'll give us minus 3x cubed. We have 3 terms with squares, so 5x squared minus 4x squared is 1x squared, minus 2x squared is negative x squared. And then with x to the 1, we have 2 terms. So that'll be plus 13x minus 10. And that is our complex polynomial function. So let's go ahead and take a look at the graph on the graphing calculator. So let's see, I think I can edit this one. So x to the fourth minus 3x cubed minus x squared and then plus 13x and then minus 10. Let's see what it looks like. Oh, that's kind of groovy. Let's go ahead and we'll adjust our window. It doesn't look like we're seeing the whole graph, so let's make y a little lower. Let's see what we get. And there we have it. So our scale, this was negative 20 and 10. And we're all set. So if you look at the zeros, right, that we were given, the real zeros were at negative 2 and 1, and the other two were complex. So do you see negative 2 and 1, and then we've got this little hump over here, which is where the complex stuff is happening, I'm thinking. Okay? All right. Okay, so here we go. Find the complex zeros of each polynomial function and write f in factored form. So this time, instead of starting from the zeros and then, multiplying everything out, we will start from the polynomial in standard form and we will, or general form, and we will be writing it in factored form. So here we go. So first step, there's going to be four complex zeros because the degree of the polynomial is 4. And second up, possibilities for P over Q. Do you see that they're both going to be plus or minus 1? So we'll just get plus or minus 1. So I don't know, I'll start with 1 and see how that goes. We don't need to graph it. There's no need for the graph. Since there's so few possibilities. So I'll just try 1. See if this works. So remember, we had x to the 4th minus 1, so you have to put in the 0 terms. So that's like 1x to the 4th, 0x cubed, 0x squared, 0x, and then negative 1. And then completing our synthetic division, we get lucky. X equal to 1 is a 0. So remember that this is 1x cubed plus 1x squared plus 1x plus 1. And so what we have found out is that f at x equal to x to the 4th minus 1 can be rewritten as x minus 1 times all this other stuff, x cubed plus x squared plus x plus 1. So factoring by grouping, we can factor out an x squared from the first, the red group there. And we're left with x plus 1. And then you just factor out a 1, and you're left with x plus 1 for the green group. And then we have a common binomial factor of x plus 1. So the depressed equation will be oops, I missed my square, my bad. This was x squared that we factored out. There we go. So this will be x squared plus 1 and x plus 1. Okay, so this is the factored form. Now to find the zeros, we'll find all real and complex. So x minus 1 is 0, or x squared plus 1 is 0, or x plus 1 is 0. So x is 1, or x squared is negative 1. If you square root both sides, you get x is plus or minus I. And then over here, subtracting 1 from both sides, we would get x is negative 1. So our zeros are, our complex zeros are negative I, negative 1, and 1. Okay. So now the last example for this section is this guy. So again, we just start our process. We have 3 complex zeros because the polynomial is degree 3. So possibilities for P, possibilities for Q. So if you just kind of come over here, 85, if you factor 85, 5 times 17. So that's not as bad as I thought it would be. So we'll have plus or minus 1, plus or minus 5, plus or minus 17, and plus or minus 85. And then possibilities for Q, plus or minus 1. So the possibilities for P over Q are plus or minus 1, plus or minus 5, plus or minus 17, and plus or minus 85. Okay, so looking at the graph, what was our graph? What was our original? So we had just positive x cubed plus 13x squared and then we had 57 at plus 57x plus 85. And let's see what this looks like. Okay, so it looks to me from this graph that this here was a scale of, remember, plus or minus 10. This was 10 and this was negative 20. X and X. So it looks to me like 1, 2, 3, 4, negative 5 might be a winner here. So that's what we'll use in the synthetic division. And our coefficients were 1, 13, 57, and 85. So here we go. And that's a winner. So writing the depressed equation, we started out with f at x is equal to x cubed plus 13x squared plus 57x plus 85. We can rewrite this as x plus 5, because x minus negative 5 is positive 5, times oh, and I forgot to put off to the side, this would be 1x squared plus 8x plus 17. So we'll get x squared plus 8x plus 17. Now, finding the zeros, whoops. We will have, we didn't need parentheses on this one, on either one. We will have x is equal to negative 5 for the first one. I'm going to use the quadratic formula for the second. We'll get negative 8 plus or minus the square root of 8 squared minus 4 times 1 times 17 all over 2 times 1. And we will have x equals negative 8 plus or minus root 64 minus 68 all over 2. So x will be negative 8 plus or minus the square root of negative 4 over 2. And we'll have x equals negative 8 plus or minus root 4 times root negative 1 all over 2. So x will be negative 8 plus or minus 2i over 2. And then writing that in the form for a complex number, we'll have x is equal to negative 4 plus or minus I. And these are our two solutions for the complex portion. And then don't forget about the negative 5 that we found before. Okay? All right. That's it for section 4.3. Have a fabulous day. I will talk to you soon. Bye.